तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we had discussed the statement of Telegrams theorem and also constructed a proof of this. And we mentioned that if we had two networks of identical topology, then we can take the current variables in one network, multiply by the corresponding voltage variables in the other network, and the sum of those products will add up to 0 irrespective of the nature of the elements and irrespective of the nature of the voltage and current variables that you are using, provided that the voltage variables satisfy Kirchhoff's voltage law in the pertinent network and the current variables satisfy Kirchhoff's current law in the relevant network. We will illustrate this with an example to start with today. We have here two networks A and B have identical geometry, in the sense that we can put each element here into one-to-one correspondence with the other elements here, and the way they are interconnected are the one and the same. That means if you represent each one of these elements by a straight line or a line, a straight or curved line, and you can represent both these diagrams by means of a structure like this, where this element A represents this 1 ohm resistance, element B in this network, and this 6 volt source in the other network. Element P stands for this 2 volt source or this 4 ohm source, 4 ohm resistor. Element C stands for the current here or the capacitor. Element E stands for this 2 ohm resistor or the 6 volt source, and likewise element D is either the diode or the inductor. So this is what is called the topology of this network. Topology is a term used to represent the geometry of a network, the way which the elements are interconnected. Therefore, these two networks have identical topology. And 5 elements are there, and you have 5 lines here, 5 curved lines here or straight lines, whatever it is, 1, 2, 3, 4, 5. Now, we would like to illustrate the Telegrams theorem here with respect to this network, taking the voltages in network A and the currents in network B. So if you find the voltages in network A, what happens is when is diode conducting or not? Suppose you open circuit at this point, then this 2 amperes goes through this, so developing 2 volts here, 2 volts here. Therefore, there is 4 volts developed across this, and this is 6 volts. That means the diode is reverse biased, and therefore it does not conduct. Therefore, the voltages in the first network can be obtained, and similarly, as far as the current network is concerned, the second network is concerned, it's a DC network. We want to illustrate this under steady state conditions. The capacitor is open circuited. Therefore, this 6 volts drives a current through this loop, and this current will be 1 ampere because 6 volts divided by 6 ohms is 1 ampere. And as far as this is concerned, under steady state conditions, 2 volts is developed here, and the voltage across this is 2 volts. So let us take element by element, find out the voltage in the A network, current in the B network, and take their product. So I have written here A, B, C, D, E, the element, pKa, the voltage of this element in the A network. A element is this, so this is 2 volts. And the current in this is in this direction, that is 1 ampere. But in application of Telegrams theorem, we must have a uniform convention. The current in an element must be normally, the drop must be in the same direction as the drop in voltage from positive to negative. Therefore, if you take this as a positive reference direction for current, the current here is upwards. Therefore, I must write this as -1 ampere. Therefore, the product is minus 2. That's how it will be. So it is important to, when you apply Telegas theorem, to have this convention. It must be consistent. The current in a particular element must be from positive reference sign to negative reference sign in all the elements, the reference direction for current, or in all elements it should be the opposite. But here we have taken the current direction, reference direction for the current to be from the positive to the negative reference direction for the voltages, right. Then take element B. The voltage here is 2 volts. The current here once again is in the opposite direction, therefore minus 1 ampere. Therefore, the product is minus 2. Take element C, that is this one. The current reference direction is like this. The actual current is opposite, but anyway that we are not worried about. But what we are interested in, the voltage across these 2 points, that is equal to 2 plus 2, 4. That's 4 volts. The current here is 0 because under steady state the capacitor does not have any current, therefore 0, the product is 0. Take element D, that is this one. This is the reference direction for the voltage, is 2 volts. The current here is 1 ampere, therefore the product is 2. Take element E, the voltage is 6 volts. The voltage is 6 volts and the current is 1 ampere, therefore the product is 6. Now you observe that as far as element D is concerned, this is positive with reference to this, but this is positive with reference to this, therefore you must write this as minus 2 volts. Minus 2. So if you add up all these sigma VKA IKB, is 0. So the sum of all these entries is 0. This is just an illustration of Telegas theorem applicable to 2 networks with identical topology but different elements. Now we would like to apply Telegas theorem to a 2-port reciprocal network. Let us consider the same network containing reciprocal elements under 2 different excitation conditions. So this is under condition A, this is under condition B. So I put VP1A, that is port voltage 1, under network A, condition A, and the corresponding current IP1A. This is VP2 port, the P2 means port 2 A, and the corresponding current IP2A. And there is a general element here inside the network, let us say impedance Z. It has got a voltage VKA and a current IKA. Let us have the same network with a different set of excitational conditions. So I have VP1B and the corresponding port current, I will call that IP1B. Similarly, I have VP2B and the corresponding current IP2B in the port. And in this element here, same impedance Z, I have VKB and the corresponding current IKB. That means we are taking the same network N and have 2 different terminal conditions. In one set I call A, the other set I call with subscript B. Now let me apply Telegas theorem, taking the voltages here, multiply by the currents here. Take this element. You have the voltage here and the current here. Now notice that as far as this element is concerned, the voltage drop here, but the current is from minus to negative, minus to positive. Therefore, I can write this as minus VP1A times IP1B, because they are not in the conventional sense, the current is not from the positive to negative difference signs of the voltage. Similarly, take this element and this current here. Likewise, Vp2A multiplied by Ip2B plus summation of all such voltages in the internal structure of network in the network N. The voltage here is Vka and the current here is Ikb, summed on all k, all the internal elements. This of course is 0. Is also equal to, take the voltages here multiply by the currents here. So here Vp1b minus Vp1b, again the same reason, because the voltage here and the current here are according to contrary to the conventional reference directions. Therefore, Vp1b times Ip1a, Vp1b times Ip1a minus again this voltage Vp2b times this current Ip2a plus summed on all internal elements Vkb times Ika. So these two both are equal. Of course, this whole group of terms add up to 0, this whole group of terms add up to 0, but that is not of interest to us. All we want to see is these two are equivalent. Now, if these are all reciprocal linear elements that we are having, Vka equals Z times Ika. So this can be written as Z times Ika Ikb, and this can be written likewise as Z times Ikb times Ik. So in other words, this whole summation is equal to this whole summation. So in this equality, this group of terms can be cancelled on both sides. This is because we have linear elements and reciprocal elements. What we have shown is here only for two terminal elements. If these are having also mutual inductances which are reciprocal two-port elements, then also this particular equality will be valid. We don't take time out to show that. It can be demonstrated. To take it for granted that this will be true even if we had two terminal pair elements which are reciprocal inside the network M. So these two are equal. That means if you take this port voltage multiply by this port current, this port voltage multiply by this port current, that sum is equal to the sum that is obtained by taking this port voltage multiplied by this port current plus this port voltage multiplied by this port current. So that is what we are having. You can cancel the negative sides on both sides. So you can write Vp1a times Ip1b plus Vp2a minus Ip2 plus Ip2b equals Vp1b times Ip1a plus Vp2b times Ip2a. This whole thing can be put in a more compact fashion. Like this. So we have a two-port network under two different excitation conditions. So we have N here. You can write, I'll remove the subscript P here. So I will write here V1A and the corresponding current I1A, V2A and the corresponding current I2A. This is the condition A, and the network, same network with the different terminal conditions. Vp1b, no longer P is required, V1b, and this is I1b, and this is V2b, and this is I2b. Then we can say that V1a times I1b plus V2a times I2b equals V1b times I1a plus V2b times I2a. So this particular relation is valid for a general reciprocal two-port network, and this is called the generalized reciprocity theorem. generalized reciprocity relation for a two-port network. And this can be used to demonstrate several results that we know. For example, special cases. A. Take I2A 0 and I1B 0. Suppose you take I2A 0 and I2A 0 and I1B 0. Then this leads to V2 I1B is 0 and I2A is 0. Therefore, it will lead to V2A times I2B, V2A times I2B. Since I2A is made equal to 0, we have only this term V1B times I1A. What this means is V2A divided by I1A, V2A divided by I1A equals V1B divided by I2B. Under what conditions? You are measuring V2A by I1A under the condition I2A is 0. I2A is 0. Therefore, this is the measured under I2A equals 0 under those conditions. You are measuring this voltage, ratio this voltage to this current when I2A is 0. Similarly, you are measuring V1B to I2B when I1B is 0. We know this is true. V2A by I1A is Z21 and this is Z12. So Z21 equals Z12 follows as a special relation of this. You can likewise put special conditions here and identify the reciprocity relation that we already know. Let me take one more example. Let me make V1A 0, V1A 0 and I2B 0. V1A equals 0 and I2B equal to 0. So if V1A and I2B equal to 0, I have V1B, I1A, this V1A is 0 and I2B is 0. That means these two terms are 0. Therefore, I have V1B times I1A plus V2B times I2A equals 0. What this would mean further is V2B divided by V1B equals minus of I1A V2B by I1B equals minus of I1A by I2A. Now under what conditions? You are measuring V2B divided by V1B under the condition I2B is 0. I2B equals 0. And you are measuring I1A by I2A under the condition that V1A is 0. So what we are having here, V2B divided by I1B when this is 0, that is the open circuit voltage transfer function G21 of S. I1A divided by I2A when this is short circuited, that is a short circuit transfer current ratio, so minus alpha 1 to S. So this is a relation which we already know. Likewise, you can also use this, take some special cases and show that Y12 is equal to Y21 and G12 of S is equal to minus alpha to 1 of S. All the relations that you know can be deduced as a special case of the generalized reciprocity relation, which we have deduced as an application of Telegon's theorem. Now let us work out some more examples to illustrate the various network theorems that we have discussed so far. Let me now work out an example to illustrate some of the network theorems that we have studied so far. We have here a network with various resistors and independent sources, DC sources, along with an element here which is nonlinear. This particular element here has got the VI relation sketched here and described by this equation. The current is 0 for V less than 0.5, that means this is the characteristic, and as once voltage exceeds 0.5, current linearly increases according to the ratio, according to the formula V minus 0.5. So this nonlinear element is connected in this network containing resistive network with a lot of independent sources, 3 current sources and 1 voltage source. We are asked to find out the values of V and I existing in this network. So networks of this type can be analyzed because one nonlinear element is involved, and it is convenient for us to calculate the V and I if we replace this entire network at these 2 terminals by its equivalent Thevenin network. Then we have 1 source and 1 resistance in series with this, then we can easily manipulate and find out the values of V and I. So this is particular example specifies a type of problem where Thevenin's equivalent is quite convenient. So let us try to find out the Thevenin equivalent of this network at the terminals PQ, of the network to the left of terminals P and Q. So to do this, let me find out first of all the Thevenin impedance, the equivalent impedance as seen from PQ. So for that purpose we have deactivate all sources. So we have only these resistances, and these are the terminals PQ. So we have to find out the equivalent resistance of this effective resistance of this 1 port network, 2 ohms, 1 ohm, 2 ohms. So for this purpose, let me say I connect a 1 volt source and try to find out the current, and that voltage divided by the current will be the equivalent effective impedance. Now these 2 1 ohms will constitute in series is 2 ohms, 2 ohms in parallel with 2 ohms is 1 ohm, and 1 ohm comes in series with 1 ohm, that is 2 ohms, 2 ohms in parallel with 2 ohms is 1 ohm. Therefore as far as we see from PQ, the Thevenin resistance or effective resistance is 1 ohm, therefore this current is 1 ampere. And this current is 1 ampere, that 1 ampere divides into 2 halves, equal halves, because this is 2 ohms and the resistance of the network to the left is also 2 ohms, therefore this current is half an ampere, and this current is also half an ampere, and again this is 2 ohms, this is 2 ohms, therefore this is 1/4 of an ampere, and this current is 1/4 of an ampere, and that current returns here 1/4 of an ampere. So this is the analysis of the circuit after deactivating all sources. So we have in the Thevenin equivalent R0, because after all this is a resistive network, we don't have to call Z0, R0 equals 1 ohm, Thevenin resistance. Now we have to find out the open circuit voltage across the terminals PQ when all the sources are acting at the same time. So we have to have a network like this. We have a 2 ampere source, we have a 2 volts voltage source, then we are having another source here, that is this one 2 amperes, and we have a 1 ampere source, and finally you have your PQ. So we want to find out the open circuit voltage. Now we can analyze this network with all the resistors that are given to us, 1 ohm, 1 ohm, 2 ohms, and this also of course 2 ohms. We can do that. But what I would like to demonstrate is that we can calculate VOC in a fairly simple fashion without having to analyze this network by using the data that is available with this analysis and using the reciprocity principle. We would like to find out VOC using the reciprocity theorem. How do we do that? Now we would like to, after all this VOC is contributed by these 4 sources. because without these sources VOC the circuit is dead, there will be no voltage. So each of these sources will contribute to VOC. So we would like to find out the contribution of VOC due to each one of these in turn. So let me do that. I will come here. Contribution to VOC so due to 2 volts voltage source. Now what we are looking for is, if this 2 volts source only is acting, all the current sources are removed, what is the voltage here? So you can say you are exciting this is the excitation, this is the response. The voltage here divided by this voltage is what we are after. But we observe here that in this circuit, after all, once everything is deactivated, suppose we are exciting this by current source of 1 ampere, the current here is 1/4 of an ampere. So it is the 2 branches. The original network is when the source is removed, that means this is short circuited. You are introducing a 1 ampere current source and you are measuring the current here is 1/4. That means the current ratio, this is a 2-port network, the short circuit current ratio in one direction equals the open circuit voltage ratio in the other direction with a negative sign. And so we can see that we know the current and this current, so this current ratio will tell us also the open circuit voltage ratio here. Therefore, due to that we can say VOC VPQ divided by 2, VPQ divided by 2 must be equal to 1/4 divided by 1 ampere. And the current direction, normally when you take a 2-port, the current direction is in this sense. Therefore, we take open circuit voltage ratio in one direction is the negative of the short circuit current ratio in the opposite direction with this reference direction for current. Now the reference direction for current is the other way around, therefore we don't have to take a negative sign. This is equal to 0.25 by 1. This will give you the contribution VPQ to this 2 volt source will turn out to be 0.5 volts. So due to, let us say, 1 ampere current source, so we apply a current at this pair of terminals 1 ampere and we would like to find out the open circuit voltage here. Now we have the result already available to us in the sense, if you apply 1 ampere across these 2 terminals, we must know what is the voltage between these 2 points. The voltage between these 2 points is half plus 1/4, half ampere, that is half a volt plus 1/4 volt. So the voltage between these 2 points is 0.75 volts. So when you apply 1 ampere here, you are getting 0.75 volts here. If you apply 1 ampere here, therefore you must also get 0.75 volts there. Therefore you can say VPQ divided by 1 ampere is also equal to whatever voltage you are getting here, 0.75 divided by 1. That means your VPQ due to this is 0.75 volts. Like this, I would leave this as an exercise for you to calculate the contributions to this 2 ampere source and this 2 ampere source. Sources 1 and 2, there are 2 such sources and you can calculate them to be 0.5 and 0.1 volt. So the total contribution to all this put together will turn out to be VOC is the sum of all this. So 1 plus 1, 0.5 plus 2, 2.75 volts. So you can complete this work and show that the total voltage is 2.75 volts. So once you have that information, now you have the Thevenin equivalent as far as the terminals are concerned. You have 2.75 volts and the Thevenin resistance is 1 ohm, and this is now connected to the nonlinear resistance here, which has got this VI relation. This VI relation. So you can say that You can solve this problem using the load line approach, which you are familiar with electronic circuits, or alternately you can do it analytically. If this is current is I, 2.75 minus I times 1 minus I, that is the voltage across this a nonlinear element. Therefore, we must find out V and I are also constrained in this manner. So simultaneously, the satisfaction of these two, whatever set of values, pair of values V and I we get, should satisfy, will be the actual voltage and current. So this is the relation. If I is 0, let us say, see whether this condition is valid. If I equals 0, you have 2.75, V equals 2.75 volts. But then if I equals 0, V must be less than 0.5. So condition A is violated. If I is equal to 0, V must be less than 0.5. If I is 0, according to this equation, V equals to 7.5 volts. Therefore, this is not a proper condition. Hence, I is not equal to 0. So it is this relation which is important for us. Therefore, I equals V minus 0.5. So when you substitute over this, you have 2.75 minus V plus 0.5 equals V. So the solution for that will give you V equals 1.625 volts. So that is the solution, and the corresponding current can be found out as 1.625 minus 0.5, 1.125 amperes. So this example gives you a nice illustration of various principles that are involved, various network theorems. We used, for example, the Thevenin's network theorem we have used, and then we have used the series parallel reduction technique for calculating the currents here. We used the principle of superposition because we found out the effect of various sources on the open circuit voltage. We used reciprocity theorem. So we have used reciprocity theorem, Thevenin's theorem, superposition theorem to calculate this answer. And we also have observed that Thevenin's theorem can be applied when the load network is nonlinear. This is an illustration of that particular property. Now let me take another example. We have a two-port network which is linear and consists of purely resistances, linear resistive network. Suppose we have a 4 volts DC source here, and the second port is short circuited. Then it is given the current here is 2 amperes and the current here is 1 ampere. This is 2 prime, this is 1 prime. This is the first port. Given this information, you are asked to find out the current that exists in port 1 when this is terminated in a 2 ohm resistor, and you are asked to find this current I when the second port is connected to a voltage source which is 2 e power minus t volts. So the same network M. Given this information, you are asked to find out the current here in this second network. We would like to apply network theorems to solve this problem. Now what we can do is, a current I flowing through 2 ohm resistor develops a voltage which is 2I. So using substitution theorem, we can say this is equivalent to another 2-port network in which we have a voltage source which is 2 times I, whatever that voltage source is, whatever that current I is, and then here we have a voltage source which is 2 e power minus t volts. And even in this case, the current here continues to be I. By using substitution theorem, we have replaced this element 2 ohm resistor by an equivalent voltage source. Now, we have in this 2-port network acted upon by 2 sources at port 1 and port 2. We can use the superposition theorem and find out the contribution to this current from this voltage source and this voltage source in turn. So by superposition theorem, by superposition principle, we have the conditions in this second network would be obtained by considering this source alone 2I volts and short circuiting the second source, plus short circuiting the first source, that is at port 1, and applying the voltage 2e power minus t volts at port 2. Now the contributions of these two sources to the current here can be superposed, and from that we can deduce I. Now you observe that in the original network 4 volts applied at port 1, port 2 shorted, will give me a voltage of 2 amperes at port 1. So 4 volts applied to this network shorted at port 2 will give me 2 amperes. So 2I volts applied to this will give me a current which is 1/2 of 2I. That means the current strength here is I. That is, you are using the proportionality principle from the original network. This is N, of course. Now as far as this is concerned, when you apply 4 volts here, short circuited current in the other port is 1 ampere. So 4 volts applied here leads to 1 ampere. That means the transfer admittance here is minus 1/4. But since the current direction is in this direction, therefore this current divided by this voltage is equal to 1/4. Now you are applying 2e power minus t volts. So this is a reciprocal network, purely linear resistive network, reciprocal network. So if you are applying 2e power minus t volts here, the current here would be 2e power minus t divided by 4 amperes. So we have the current due to this source is 2e power minus t over 4. The current due to this source is I. The sum of these two currents must indeed be the current that we are looking for. So from this we equate the sum of these two to this. So the current flowing in this direction, this I equals the current flowing in this direction is 2e power minus t upon 4, that is the current here, plus the current here, but the current is now in the other direction, therefore minus I. So this is the equation, the sum of superposing these two currents, you must get this, and this leads me the result I equals e power minus t upon 4 amperes. So that is the answer for this question. Now since this is a purely resistive network, there is a proportional relationship in time domain between the current and this voltage. So we didn't use any Laplace transformation technique here, because it's a non-dynamic network, resistive network. The current and the voltage are proportional to each other in the time domain, whereas in a dynamic network such proportionality arises only in Laplace transform domain. But here it's a purely resistive network, so we didn't use Laplace transformation technique. We know the current here is proportional to this voltage in time domain itself, therefore we didn't use Laplace transform. So finally the answer is I equals e power minus t over 4. So in this example we have used superposition principle and the reciprocity principle. So this is an illustration of how the network theorems can be applied to find out the required result in a particular case like this. In the last few lectures we have considered various network theorems, and we discussed the various the characteristics of the various theorems and illustrated them with examples here and there. Now it's time to work out an exercise, and I'll give you a set of problems which you may work out, and these problems illustrate the various network theorems that we have studied so far. Problem number 1, we have essentially a DC network in which there are three independent sources, 2 voltage source and one current source, and we have 2 dependent sources, one voltage source and a current source, both dependent on the control voltage Vx. So you take down this particular figure and use superposition theorem to evaluate Vx in the DC network shown. So in this DC network we have 5 amperes current source, 6 volts voltage source. Vx is the control voltage which controls this voltage dependent current source, and this voltage dependent voltage source. And we have 20 ohms resistors, 10 ohms resistor, 6 volts voltage source, and of course 8 ohms resistor. So use superposition theorem to evaluate Vx in the DC network shown, and when working this out, you should keep in mind when you are deactivating the sources, you should deactivate only the independent sources. That means you must analyze this network with 5 amperes working alone with the dependent sources intact, 6 volts acting alone with this and the other one deactivated, and the other 6 volts. That means 3 repeated analysis you have to make and superpose these effects to find out the total voltage Vx as a contribution of the 3 individual sources. This is problem number 1. In problem number 2, you have essentially a parallel connection of 4 branches. When the switch is closed, the switch S is closed at t equals 0 after steady state is reached prior to the closure of the switch. So when the switch is open, there will be a current, there may or may not be a current in the inductor, there is possibly a voltage across the capacitor, so you have to use the initial conditions. And once the switch is closed, 4 branches come in parallel, so you can use the transform diagram approach for solving this problem, work out in the Laplace transform domain. You find out IL of t in the load resistance RL using Norton's theorem. That is one method of solution. The second method of solution is when the switch is open, there will be an open circuit voltage across the switch. So you replace this by a voltage source using substitution theorem, and when the switch is closed, you have to put another voltage source which is the same magnitude at the opposite side in series with that, and use the superposition effects and find out the current IL of t again using by superposing the effect of each one set of sources with another voltage source. So this is again an illustration of the application of a network theorem. So you find out IL of t using both these methods and compare the results, and this should be worked out again in transform domain. Again, let me say this 2 volts 1 Henry, 2 volts 1 ohm, 2 volts 1 farad capacitor. The switch is kept open for a long time till steady state is reached, and then it is closed at t equals 0. You have a load resistance RL as 1 ohm. So you have to find out the current IL here. The third problem, again this is an analysis of the transient solution in a particular network. S is closed at t equals 0 in this network after steady state has been previously reached, and you are asked to find I of t in this shorted switch, and you have to use Thevenin's theorem for that purpose. The source is 12 volts 1 ohm 1 Henry, 0.5 ohm 1 farad capacitor, and so you have to calculate the initial currents in the inductor and the initial charge in the capacitor, use them, and then find out the open circuit voltage here. Then looking in impedance, set up the Thevenin's theorem, Thevenin's equivalent circuit, and find out the current in this shorted branch. That is the third problem. Problem number 4, copy the circuit. It has 3 parallel branches, 3 1 volt sources. This polarity is of course reversed, and you have a 2 Henry inductor, 2 ohm resistor, and 2 farad capacitor. Assume 0 initial conditions in the circuit and find out the voltage across these 2 nodes. Find VAB of t for t greater than 0 using Millman's theorem, because this is the tailor-made for Millman's theorem application. You have 3 parallel branches with independent sources, and you also put initial condition sources whatever they might be, and find out VAB of S, and from that VAB of t. Assume 0 initial conditions. Of course, initial condition sources are optional because the 0 initial condition. That means capacitor and inductor are not charged to start with. Okay, that is first problem. That is problem number 4. Problem number 5. You have a linear reciprocal network N with 0 initial conditions. So when port 2 is short circuited and you apply 2 volts at port 1, close the switch at t equals 0, current I1A and current I2A in the two ports are given by these expressions. I1A of t is 1 minus e to the power of minus t times cos t minus sin t, whole thing of course multiplied by u of t. I2A t likewise is 1 minus e to the power of minus t cos t plus sin t multiplied by u of t. These are the two currents that are given here. So from these conditions we contemplate this network, the same network N is now excited by a 1 volt source at port 2 with a 1 volt source switch closed at t equals 0. No initial conditions in the network N once again, and port 1 is shorted through a 1 ohm resistance. So you find I1B here using the data that is available in the first set of excitations. This is all one set of excitations. Using this in the second set of conditions, find I1B for t greater than 0, again using possibly reciprocity theorem, possibly substitution theorem, whatever, and superposition principle. So find I1B of t in the second set of excitation conditions using the data in the first set. Sixth problem, you have a network comprising Z1, Z2, Z3, Z4, Z5 linear elements, and they are excited by, that network is excited by two sources, a voltage source EFS and a current ISS. So these are the sources in the transform domain. You are asked to you have to find out the open circuit voltage at these two terminals. Now one way of arriving at the open circuit voltage V0 of S would be not to analyze this circuit as such, but to take another possible circuit like this. The passive portion is the same, Z1 of S, Z2 of S, Z3 of S, Z4, Z5S, but you excite this by a current source IE of S equal to 1. So in the transform domain, that IE of S is equal to 1. So if you use that current source and measure this voltage Vj of S here, that is where our current source was present earlier, you measure this voltage Vj of S, calculate this, and calculate the current. Because of this voltage source is replaced by a short circuit, calculate IE of S. So you calculate Vj of S, the open circuit voltage across the terminals of the old current source, and the short circuit current through the old voltage source location. So you analyze this network and find out these quantities, and now you are asked to show, use Telegen's theorem to both these networks to show that V0 of S, that what we are interested, is obtained by Vj of S times Is of S minus IE of S times E of S. Vj of S is this voltage, IE of S is current. So since you have calculated these two quantities and you know the strengths of these sources, you can calculate V0 of S. So instead of analyzing this network, we should be able to calculate V0 of S from this information. Now use reciprocity theorem to deduce the same result. So you derive this result using Telegen's theorem on one hand and reciprocity theorem on the other hand. So these are the two parts to this question. So take down these figures once. Okay. One more problem. Problem number 7. What is the galvanometer current when Rx equals 3 ohms? The circuit is, we have a 4 volt source here, 6 ohms resistor, another 2 ohms resistor, and you have a resistance Rx, unknown resistance, a galvanometer whose resistance is 10 ohms, and a 1 ohm resistor. So find out the galvanometer current when Rx is equal to 3 ohms. Use compensation theorem to deduce the galvanometer current when Rx equals 4 ohms. So if the Rx value is changed from 3 ohms to 4 ohms, what would be the new galvanometer current? So this is an illustration of the application of the compensation theorem, a similar example which I worked out in our lecture earlier. So this set of 7 problems in this exercise will provide you enough scope for having some practice in applying the various network theorems that we have discussed in our 2-3 lectures on network theorems which were covered so far, that have been covered so far.